Okay, so I fell down a bit of a rabbit hole trying to understand what some of the direct methods of calculating the mass of the stars in a binary system that the paper was referencing to were. Uh, if you do some googling regarding this, one answer that will pop up is Kepler's third law, and that's actually slightly confusing, as Kepler's third law basically just says this, that these two are proportional. Then Isaac Newton came along and built upon that, and later on we've started to refer to this expression as Kepler's third law. So let's not get stuck in why that is the case. This is the relationship we're talking about when we're talking about Kepler's third law. So the mean distance to the center of mass, the period, the masses of the two stars. And if you calculate this, you'll have two unknown variables, the separate masses of each star, but this relationship between these two is the same as the relationship between the radius of each star to the center of the mass of the system. So you can look at the radius of that, substitute it in, and then you can calculate the masses for the separate stars. So that's one of the direct methods, and it's direct because you can measure these directly. That's what is meant by directly. Of course, your calculation will only then be as accurate as those measurements of these variables. All right, so we are back at the determination of masses of eclipsing binary stars, which is this review from Daniel M. Popper from 1967. I wanted to check what direct methods were when he was referring to it, and I don't think I know every direct method yet. There might be more, but at least one of them is what we discussed regarding Kepler's third law. So I'm gonna push on and see where we end up. So we read this before, so I'm just going to mention some stuff. Direct methods of determining stellar masses are available in three cases. So these are not three different methods. It's just these are the cases in which the direct methods are available to use. So number one is visual binary with visual orbits analyzed, mass radials evaluated, and parallaxes determined by geometrical means. That's kind of what we've been discussing exactly. Double line eclipsing binaries with light and velocity curves analyzed. Visual binaries with visual orbits analyzed and the radial velocities of the components measured. So I think what you can do here is, if you have the velocity, the radial velocity, you can use that to also with Kepler's third law. Where you substitute it as the centripetal force, and then you can use the same equation as before. Here they mention, insofar as mass determination itself is concerned, visual binaries suffer from the difficulties inherent in determination of small angular quantities. I'm not sure if they are referencing to the parallax here, but yes, it's your mass determination will of course depend on the accuracy to which you can measure the, well, I don't know if small angular quantities, but the distances, for example. So the semi-major axis, which is what we have in the third Kepler's third law. If these spectrograms are properly interpreted and the measurements of velocity are made on spectrogram of adequate dispersion, the errors of mass determination may be quite small and free of systematic effects. Okay, so you can use the Doppler shift in order to get the radial velocity. I think that's what they're saying. On the other hand, the luminosity and position in the HR diagram, that's a diagram which on the one axis has luminosity and the other has temperature. Apparently the types of stars kind of maps out. There's like a negative slope on there, and it's essential for the interpretation of masses. Apparently, its position is more readily obtained for visual binaries. That is to say, when you can see that there are two, directly see that there are two stars, rather than eclipsing binaries. That's when you can see that there's two stars in the system by the fact that they are eclipsing each other. In the remainder of this section, brief comments will be made on methods other than the two principal methods, which are discussed later in this review, and in the discussion of visual binaries by Egan in an accompanying review. Okay, the great importance to the third direct method in spectroscopic observations of a visual binary. So, okay, I think they're talking about this. So they're talking about it now as three different methods. Brief comments will be made. Okay. The third is one that may obviate the need for accurate trigonometric parallax. Okay, so for that one you might not need the parallax, which might be why you don't need the very small, the difficulties inherent in the determination of small angular quantities. The conditions for useful application of this method are fulfilled in relatively few cases. The same precautions necessary in interpreting and measuring the spectrograms must be employed as for eclipsing binaries in order to avoid systematic effects. Difficulties with velocities of the hotter component of alpha hour are well known apparently, because of the usually small difference in velocity of the components. Because of the usually small difference in velocity of the components. Okay. Is the components here? Is that the stars? The highest possible dispersion should be used in this method. Even if velocity differences are obtained with high precision, the masses will not be well determined unless the elements of the visual orbit are adequately known. In addition to the period, okay, the semi-major axis, lowercase a, the inclination, the velocity difference may depend critically on the period, and omega, the radial velocity. A case in point is delta EQ, for which the difference of velocity has been carefully measured, but the elements, the period and the radial velocity are not well known enough for a substantial improvement of the masses. Okay, what is P? There are several indirect methods that have been employed for mass determination. For visual binaries with orbits analyzed, there are moving group parallaxes, photometric parallaxes, and parallaxes from H and K line widths. For single line eclipsing binaries, the mass of the more luminous component may be assumed from its spectral type in order to evaluate the mass of the secondary component. Analysis of the spectrum of a single star may furnish its surface gravity and effective temperature from which the mass may be evaluated if the luminosity is known. The virial theorem has been employed for evaluating masses in star clusters. So they're talking here about indirect methods, and then it's spectrographic measurements in part that they're using, and some other stuff, moving group parallaxes, photometric parallaxes. Okay, so it's just so parallaxes. Well, I mean, I thought you used the parallax. The reason why we're interested in the parallax is to be able to say what the semi-major axis is. And for that, we need the distance. And to get the distance, we use the parallax. So all of the, I don't know if they're here, they're just talking about different ways of estimating the parallax. And then here it talks about analysis of the spectrum of a single star may furnish its surface gravity and effective temperature. And then I think by using this HR diagram, which we were talking about, you can estimate the mass. Of course, I haven't dived into that, but I can see how it's you would need to examine it critically if you want to really understand your estimation and how accurate it is. And the paper review continues. Every application of an indirect method of mass determination needs to be critically examined from three standpoints. How valid is the hypothesis upon which the calculation of mass is based? For example, in the use of H and K line widths for parallax, is the relationship between line width and visual luminosity unique, independent of all other properties? 2, how well determined are the numerical parameters of the method? For example, how precisely is the relationship between line width and luminosity known? And 3, how well determined are the observed quantities required for the particular application? For example, how well determined are semi-major axis and period of the binary orbit and the H and K line widths? For some critical problems in the interpretation of stellar masses, parallaxes of visual binaries must be accurate up to 5%. Since relatively few trigonometric parallaxes are determined as well, the use of indirect methods is attractive. Okay. So, I see. Okay, so the usual parallax way, I guess, is trigonometric. And apparently they're not determined that well. But 5% in parallax corresponds to 0.1 magnitude in absolute magnitude, the precision required in photometric and H and K line parallaxes. It is open to serious question whether the uniqueness and observational accuracy of the calibrating relations color luminosity and line width luminosity are established more precisely than 0.2 mag. As an example of the uniqueness problem, one may refer to calculations of the effects of chemical composition on position in the HR diagram. A change in the helium abundance by a factor of 2 corresponds in the calculation cited to a change of about 1 mag for a given color. Similarly, each parallax determined by the moving group method and used for mass determination must be critically examined to evaluate its uncertainty and validity. The use of these indirect methods of parallax determination for studying problems other than mass determination is subject to less stringent demands. Okay, yeah. So I think the reason why we want the parallax is to be able to tell the distance to the star so that we can say something about the semi-major axis, so that we can get this one accurate. And apparently the trigonometric parallax is hard to get that accurate, so therefore we're looking into other ways of determining the parallax effect. Determination of surface gravity and indirectly the mass by spectroscopic analysis of single stars would be of particular importance for evolved stars, for which our knowledge of masses is very incomplete. Okay, so this is an indirect method that I don't know of. I mean, it feels intuitive that you could say something about the mass from the gravity, but how do we know the gravity? How would you know the gravity of the star from afar? But it's just for such stars that our knowledge is also incomplete concerning the structure of the outer layers where the observed spectrum is formed. With respect to the use of the virial theorem, hypotheses include the assumption that the velocity dispersion may be obtained from a few of the brightest stars, the absence of appreciable invisible matter, and the mass distribution in the cluster. So I need to look up what this virial theorem is. In each of the indirect methods, the validity of the hypotheses and the uniqueness and determinacy of parameters are likely to be matters of opinion. The usefulness in the eyes of a reader of masses determined by this means will depend on his opinions and on the purpose for which the masses are to be employed. This is interesting. That's interesting. Only masses determined by direct methods will be reliably enough known to be useful in elucidating some of the more critical problems of stellar structure and evolution, particularly for stars on and near the main sequence. The position of a star in the theoretical HR diagram is very sensitive to its mass. Likewise, the delineation of fine structure in the mass luminosity diagram requires masses of high precision. Unless a valid estimate of the uncertainty in the mass of a star is available, its usefulness for studying such critical problems will be limited. The linear scale of the orbit of a binary star is the critical quantity for which estimates of systematic and accidental errors are essential. I don't get that. The linear scale of the orbit is the critical quantity for which estimate of systematic and accidental are essential. Okay, I read that a bit wrong. So when they mean here the linear scale of the orbit, they're just talking about the orbit in normal distances rather than just talking about it in angular velocities or so. So they're talking about it, okay, the actual, kilometers or whatever you want to use, right? That's why we need the parallax. That so we can estimate the distance, so we can say something about the linear scale of the orbit. So the linear scale of the orbit of a binary star is the critical quantity. Yep. For which estimates of systematic and accidental errors are essential. Yeah. Okay. As discussed below, these estimates are obtained readily for the eclipsing binaries, in which the only critical quantities are the amplitudes of velocity variation. For the visual binaries, the orbital elements, parallaxes, and mass ratios for unequal components enter. Evaluations of the systematic and accidental uncertainties in the major axes based upon these quantities are not straightforward and are usually not attempted. Several important contributions have been made by Egan, who has shown that the quantity of the semi-major axis cubed or the period squared may, under favorable circumstances, be determined with greater precision than would be expected from the separate uncertainties in A and P. I don't know what A double apostrophe means. He also has attempted to assess the determinacy of the orbital elements for a number of systems, but for which the visual binaries in general, because of the complexity of the way in which the different kinds of observations enter determinations of mass, valid estimates of uncertainty have not been carried out. This lack is an important weakness in the availability in the available data on masses from visual binaries. So I don't know why the estimates are obtained readily for eclipsing binaries. The only critical quantity is the amplitude of the velocity variation. I'm not sure. I have a guess. For the visual binaries, the orbital elements, parallaxes, and mass ratios for unequal component center. Okay, that makes sense. I thought you'd need that for the eclipsing binaries also. But maybe it's enough with the radial velocity and you can get that through the Doppler. And you can't do that for the visual binaries because you can't determine which star has what effect on the spectrograph. Okay, moving on. Mass determination of eclipsing binaries introduction. Since the discoverings by Pickering of double lines in the spectrum of Zeta Ursa Major, I think you say it that way, and by Vogel of the velocity variation of beta pair, the principles of mass determination in spectroscopic binaries have been clearly understood. The quantities required being radial velocities of the component and the orbital inclination. So the inclination here is the inclination of the orbit towards Earth. So the way that I understand it is what you're interested in is the radial velocity. But however, of course, if we want to measure that, the inclination is going to affect that. So if it's perfectly edge on, it's easier to measure the radial velocity. But if it's offset a little, then we can't tell that. But here he is saying that we need this quantity as well. I'm not sure what he means by that, or maybe what he means is we use this to calculate the true radial velocity. With respect to the latter, after increasingly valid attempts by Myers, Roberts, Schlesinger, and Baker, and Stebbins, a general solution for the inclination and other elements of the light curve was given by Russell. Numerous modifications and improvements of the Russell scheme have been proposed and employed. But if we restrict our discussion to eclipsing binaries, for which radii might be evaluated from the light curve, uncertainty in the orbital inclination is generally a minor cause of uncertainty in evaluating the masses of the components, as is uncertainty in the orbital period or eccentricity. Another minor, although systematic effect is the correction for the effect of reflection in a closed binary. For the effect of reflection, I don't know if that means that the light reflects onto the other star in a closed binary. Thus, the central problem in determining the masses of the components of eclipsing binaries is, as it has been since the beginning, simply that of evaluating the amplitudes of velocity variation of the two components. Okay, I had some troubles with the recording. Basically, I've been reading this part, problems in measuring the radial velocities. He's talking about problems and trying to figure out what the radial velocities is and doing that via the spectrographic measurements. So he says that when interpreting these measurements, one has to make two decisions. First decision is whether or not it's actually a real line that one's seeing, or if it's a grain in the spectrographic measurement. This is how it looks. You can see it's kind of hard to tell, or you can imagine that in some cases it would be hard to tell if it's a line or if it's a grain. Additionally, he talks about the second addition, which is how do you assign what line corresponds to what star. A line which is in reality an intrinsically weak line, and the more luminous component may be mistakenly assumed an intrinsically strong line on the fainter component. Improvement in the spectrograms over the years, particularly in the dispersion available, has made it possible to make these decisions with greater certainty. In the past, numerous mismutations have resulted from difficulties mentioned. The third catalog of spectroscopic binaries in 1924 lists 13 eclipsing binaries in mass determined by a combination of photometric and spectrographic data. It is now clear that for only 6 of these were the lines of the beta component measured unambiguously. Okay, so there's 13 eclipsing binaries discussed in this catalog, but after, I guess, further examination, it was clear that 7 of these they had taken some of the lines that actually corresponded to the stronger component. They took to be come from the fainter component. A recent compilation lists 42 eclipsing binaries with well-determined absolute dimensions. Brief comments on each of them have appeared elsewhere. Of these 42, at least 6 are systems for which the velocity variation of the fainter component is either unknown or very poorly determined. A still more recent discussion of eclipsing binaries containing an even larger proportion of undetermined or poorly determined absolute dimensions, resulting from difficulties in interpreting the spectrograms. Thus, its appearance in the literature does not always provide assurance that a radial velocity results from measuring real spectrum lines belonging unambiguously to the component in question. Because of the difficulties of interpretation, it would be helpful to the interested viewer if high-quality reproductions of all spectrograms of double-line binaries were published, along with the results of measurements of the spectrograms. For a number of good reasons, such reproductions are not generally published. If one has questions concerning the interpretation, he must usually examine the original material himself or obtain new spectrograms. Both procedures have been employed in my own studies. A difficulty of interpretation of a different kind, which shall not be referred to further, is that the absorption lines measured may be produced in part by atoms having mass motions systematically different from that of the stellar photosphere, as discussed by Struve and others. These effects reveal themselves by inconsistencies in the results be that can usually be recognized. The associated problems are discussed elsewhere. To illustrate some of the problems of interpreting the spectrograms, it may be instructive to examine a particular system. TV set is a 9-day eclipsing binary, magnitude 9.0 photographic, node spectral type F2 approximately on the main sequence. The secondary component is clearly present in the spectrum, but its lines are weak, so that the difficulties of interpretation referred to are quite severe. In the case of Z, Her, and RSCVM, similar difficulties were circumvented by observations in the visual region of the spectrum. TB set is less favorable for effective use of this technique because of its faintness, but because its secondary is of earlier type, G0 question mark, than in the other systems, so that lines in the visual region are not strong, and because interstellar components cause difficulty in measuring the weak D lines on the secondary. Hence, photographic region must be relied upon. Figure 1 shows a spectrogram, original dispersion 21.5 angstrom per millimeter, obtained at the phase of maximum velocity of recession of the more luminous component. While effects of line doubling are clearly evident for a number of lines, examination of spectrums of higher dispersion, 10.2 angstrom per millimeter, shows that it is only with difficulty that unblended lines of the fainter components suitable for meshing can be found. Figures 2 and 3 show enlargements of 2.2 angstrom per millimeter spectrograms of TB set. I need to check this video. No, this is video 1. Zeta, lambda, 4,004.4, 0.4, 0.7 is original dispersion. Okay. Yeah, this tells me very, very little. I also don't know how these would have looked in print and how it looks, because obviously this has been scanned from this PDF that I'm reading. So, yeah, there's some, I don't know if this is the lines marked out, maybe? He's marked out the lines for us. Um, the second component is clearly present, but its lines are weak, so that the difficulties of interpretation to are referred to are quite severe. In the cases of Zeta, Her, and RSCVM, similar difficulties with circumvented to Zeta is less favorable for effective use of this technique because of its faintness, because the secondary is a variable type, and because hence so obtain at best shows there is only difficulty. Yeah. So one near each node together. So the feature of the stronger component T set is in the corresponding Fisher interaction. The lines of the weaker component are displaced to the red in the upper top to the right. Okay. So lambda 40, 45, okay. 40, So let's see if we can figure something out. I think here he's referring to, so this is like a wavelength 40, 45 ohms, maybe. I don't know. And he says that it's good, as if it's clear. So let's check for that. If we can see, oh, there's no numbers. So we have the letters, maybe. Okay, so this is A. Yeah, okay. There's clearly a line there. So let's see, what does he say? Good when displaced to the red, but blends badly when displaced shortward. Mm, okay. Blends with a 9 when displaced to red. Okay, so he's talking about this line when it's being red shifted. Is that what he's saying? So it's good when it's displaced to red, but blends badly when displaced shortward. And that's above and below. Hmm. Okay, so so he keeps on talking about the different lines here, which ones are good and which ones are bad. I'm not really sure. I don't really know how to read these. I don't know if he's looking at a series of them or if he's only interpreting this one snapshot. I also do not know how the scanning has affected these pictures, so I'm just gonna go ahead and skip that part. He continues, a total of 13 lines of the weaker component per plate was found suitable for measurement when displayed shortward, and 8 when displayed longward in the wavelength region 4000 to 4600. Use of these lines should produce velocities free of systematic error. Now he's talking about systematic error and another type of error, which I don't remember what he called it, but it's funny that okay, he's sure of that now. Although spectrographic investigation of the system is not yet completed, about 12 spectrograms obtained at suitably distributed phases will determine the amplitudes of velocity variation to a position of 1 or 2 kilometers per second. Preliminary values are K1 69 kilometers per second, K2 74 kilometers per second, leading to minimum masses of 1.45 and 1.45 and 1.35 Earths, sun masses, somewhat larger than the values given for the system on the basis of a less satisfactory analysis. A definitive light curve is badly needed. Okay, so I don't know if he means that we need a light curve because it's larger than the analysis that was done before, so he wants a light curve because they differ. But I would have loved to see, just so I can be sure, what um, calculations were done. Okay, I get this, the measurement. So, but I would have loved to see just to be to get a to be certain in my understanding of this, how they went from these measurements these to these velocities and then to these masses. Of course, I think it's Kepler's third law, but it would have been nice to see. Another example is V805 Equil A2 figure 4 temperature. Here. Okay, so more measurements. I'm gonna take a look at this. Okay, I had some issues with the audio or with the microphone. Apologize for that. I was using the wrong microphone. So, anyways, another example is V805 Equil A2 figure 4, 10.2 angstrom per millimeter, while the hydrogen lines are clearly double. Okay, let's see if we can find that. It may not be assumed that they can be measured without systematic effects resulting from overlapping wings. What do they mean by wings? What wings? So double lines, hydrogen double lines. Okay, I thought I could find maybe a pair. I should look up how to read these. Unblended lines are clearly belonging to the fainter component. Unblended lines clearly have not been found in the photographic region. The D lines, figure 5, are each triple, the central component being interstellar. The dispersion shown, 20 angstrom per millimeter, in the visual may not be adequate and the star is too faint. 7.8 mag for much higher dispersion. Use of an image tube may be advantage in such a case. A third example is the 6th mag B star U of figure 6. While the He lines are suitable for measurement, the H lines are not. Even with such poor lines as the helium lines, as a matter of fact, they are unusually well defined in the U of insofar as the B-type spectroscopic binaries are concerned. The relatively high dispersion of 10 angstrom per millimeter is probably preferable to lower dispersions. When the lines are not very deep, irregularities in the grain pattern of the spectrograms have less influence on the measurements with higher dispersion. In a system of this character, the number of lines per spectrogram satisfactory for measurements is small and varies appreciably from plate to plate. I don't know how they do these spectrographic measurements plate to plate he's talking about. I wonder how it's done today. Furthermore, the plate error is small compared to the uncertainty of the position of a line. Under such circumstances, it's probably preferable to compute the amplitude of velocity variations from measurements of the individual lines rather from the mean velocity for each of the plates. Okay, so here he indirectly told us, finally gave us some hint into how the velocity variation is calculated. It's from the mean velocity for each of the plate, and that's distinct from looking at the individual lines. So I guess they do some sort of calculation for each and every of these little line for an entire plate, and then they take the mean of that for when they say that, okay, this is the velocity of this star. Maybe, I don't know. The spectrograms reproduced were all obtained at the Mount Wilson Observatory. While the system illustrated here are representative, every system has its individual problems that must be attacked in an appropriate manner. Reference made to the literature for other examples. Even when the lines of both components are of comparable strength, it may be clearly visible so that there's no ambiguity of interpretation. Systematic effects on the measured velocities will result if inadequate dispersion is used. The usual effect, well known to the workers in this field, is that the separation of the lines are measured in greater on lower dispersion plates. In order to avoid such effects, dispersions of 10 angstrom per millimeter or higher are desirable, while dispersions appreciably lower than 20 angstrom per millimeter are probably inadequate except for B stars or perhaps for systems with stars of greatly different spectral types. Okay, so you can distinguish them. So that the two components have essentially different sets of lines. The hydrogen lines can be measured safely only in stars of types about F5 and later, where their wings are sensibly absent. Okay, F5. The procedures used in computing the amplitudes of velocity variations as well as other elements are of relatively minor importance if the measurements are valid and free of systematic effects, and if the observations are suitably distributed in phase. The method of least squares, has the advantage of being well defined and of yielding internal uncertainties of the elements. In order to conserve observing time, which is severely limited, observations need to be concentrated near the times of nodal passage. Then the amplitudes will be determined with the greatest weight. In such a case, the weight of determination of E, I think that's the eccentricity, and omega is generally low. Maybe not omega, because that's what we want, right? We want the radial velocity. So I think maybe this is some sort of angle or so. While uncertainty in E and omega has a negligible effect in evaluating the masses, it does reduce the value of the observations for studying other problems, such as apsidal rotation. In any event, these problems are generally better studied in single-line binaries, where the effects of blending of the lines of the components do not influence the measurements at the critical phases of rapid velocity variation. A program of investigation is the next part, called by 1934. Sufficient photometric and spectrographic work had been carried out on ecliptic binaries for ABYs to undertake a survey of the results. A difficulty that he emphasized was that many systems the spectral types published for two components were much more nearly equal than would be predicted from the depths of the minima of the light curve. It was this difficulty that first led me to investigate several well-known systems. It was found in a number of cases the discrepancy was not a physical one, but resulted from the misinterpretations of the spectrograms of the kind referred to above. Okay, so that's interesting. I mean, I did get the sense this is the first or for one of the first papers that I kind of read in this field, but I did get the hunch that this guy was very careful, and it does seem now also that he has been more careful than perhaps others have been when interpreting these spectrographic measurements. So that's interesting, and I appreciate that. It's just too bad that there's so much going on that I don't know of. That is, the lines used for estimating the spectral types of the fainter component are too weak for one to be certain of their presence, or are badly blended with lines of the stronger component. This is not to imply that there may not be real discrepancies between spectral types and surface brightness, particularly among the B stars. One may refer as an example of the discussion of Alphavir by Struve and others. Once the reasons for the incorrect assignments of spectral types were understood, it followed that the masses of the components in such systems had not been soundly based. Hence, a re-examination of the masses was undertaken. In some cases, it was concluded that the systems were not suitable for mass determination. In others, improved material led to re-evaluation of the masses, with results sometimes in agreement and sometimes in significant disagreement with the earlier ones. During the first stages of this work, a little more than 10 years ago, theories of stellar interiors and stellar evolution were developing to the degree that, if significant tests of theory were to be supplied, existing data on the masses of eclipsing binaries needed to be assessed critically and increased. If the ensuing expansion of the observational program, it was found in the ensuing expansion of the observational program is found that other effects not associated with difficulties in the spectral types could lead to significant errors in the masses. These include various effects due to the use of inadequate dispersion and of inadequate measuring techniques. Some of these effects have been illustrated above. A number of results from this program, which is continuing, have been published in the reference cited. It is now clear, as discussed elsewhere, that in order to provide significant information in discussion of such critical problems as the dichotomy of the mass-luminosity relation for mass-sequence stars, the amplitudes of velocity variation must be known with accidental and systematic errors of 5% or less. how can we know about the magnitude of accidental errors is something that I wonder, but okay, let's leave that aside. In re-investigations to date of stars of type A0 or later, systematic corrections of the earlier observations of considerably more than this amount have been required in a number of cases. It should not be inferred that the only systems to be studied are those previously investigated by others. A number of promising new systems that are being worked on will be referred to later, but most of the known double-line binaries brighter than about 9th mag were observed spectrographically in earlier decades, and even with the most powerful equipment now available, it is not possible to obtain adequate spectrograms for stars much fainter. As discussed above, grading dispersions of 10 angstrom per millimeter or higher are recorded in many cases, and dispersions lower than 20, except perhaps for some of the B-type systems, are inadequate in most cases. With the Coudé spectrographs of 100 and 120-inch telescopes, the useful limiting magnitude is about 10.5 at 20, and 9 is about to 10.5 at 20 angstrom per millimeters and 9 at 10 angstrom per millimeter in the blue and violet region of spectrum. If one must employ the visual region to observe the lines of the Fender components, the useful limiting magnitude is 8 to 8.5, except for systems of long period. All right, so we will continue in a survey of systems. I do have to say that I think the next paper I will choose will be a paper from a different author than Daniel M. Popper. Not that I don't appreciate him, but I do want to get the many perspectives on this. And as we saw recently, I think it was here, yeah, he talks about that some errors or some misinterpretations of the spectrograms made by other papers, and I thought that was really interesting. I do get the feeling that this guy is very, very careful, and that's the kind of offer that I also want to read. That's what I went into, but realizing now that that's also the type of offer that will spend a very long time just talking about the different, for example, resolutions you need on the spectrograph and so, and that is interesting. However, this paper is from 1967, so I don't want to spend too much time trying to understand the limitations on the technology or the methodology in 1967. The reasoning behind all of these estimations of the mass and so are the same as in 1967, so that's interesting, but the limitations of their instruments is not as interesting. So, but I'm gonna push through in this paper and then see what we'll do afterwards. So, a survey of systems. In this survey, reference is made to double-line eclipsing systems that are or may become useful in providing definitive determinations of stellar mass. If the system is to be of value, the radii and colors on a standard system of the component must be known in order to place the stars on the HR diagram or its equivalent. Systems such as the W Ursa Major stars and other contact systems are not included in the discussion. References to the literature for the systems mentioned may be found in such works as Basic Astronomical Data, okay, list a lot of works. And then there's another topic here, main sequence stars of type G2M. The only well-observed system on this group particularly valuable for comparison with visual binaries are YY Jam M1 and UV Leo G2. BH Ver has properties much like those of UV Leo, but with the components more unequal in temperature. ABT 47. Okay. So what's he doing here? It will be very difficult to investigate this system with higher dispersion because of its faintness and short period. ER Vol may also be similar to Jubileo, so he's talking about, I think, all of these different stars, and he's talking about the data that you can find here regarding these systems, and then he's evaluating whether or not it's helpful to, if we can know the radii and the colors so that we can place it in an HR diagram. Maybe that's what he's doing. And now he's talking about the main sequence stars of type F, also in these works. There's a considerable photo material both. It's easy, but yeah, it's one of the. It's the question of the dichotomy of the mass, but also to establish the magnitude and sign of the ultraviolet excess, since one of the outstanding current problems is the question of the dichotomy of the mass luminosity relation discussed by again. Okay, that sounds interesting. There's a kind of a, hen or the egg type of problem that I can sense there will be regarding when you're talking about, the luminosity and the temperature of these, and the radii even maybe of these stars. What's your little clue into being able to estimate the first of these variables? Anyways, he goes further now, talking about main sequence stars, early A stars, system among the A stars, B stars, B stars, examples of system with favorable spectral light, but curves not suitable for determined solution. Okay, he's talking about that. So the only way this would be interesting is if I would actually have the data, and it's too much work to find that. I can't be bothered. If it was here in front of me, I'd have a look. So yeah, AR systems in which cool giants and supergiants. The very meager information available has been reviewed elsewhere. Peculiar systems. This survey has been considered system for which the masses may be determined unambiguously without difficulties caused by absorption in gaseous envelopes and streams. Estimated masses are available for a few of the numerous peculiar systems. Cataclysmic variables. Wow, okay. Disk and halo stars. I'm unaware of any other characteristics of motion eclipsing binaries in space and minor systems not belonging to the spiral arm population. It's not known whether the eclipsing binaries supporting globular clusters are foreground stars or cluster members. Wait, what? I'm unaware of any study of the characteristics of the motions of eclipsing binaries in space that might reveal systems not belonging to the spiral arm population. The spiral arm population. It's not known whether the eclipsing binaries reported in globular clusters are foreground stars or cluster members. Okay, I'm gonna have to look that up. Some observational results. As discussed here, it has been found desirable to re-examine the spectrographic observations of all eclipsing binaries in order to evaluate their suitability for mass determination. Because of the relatively small amount of observing time available for the spectrographic program, and because of the vagaries of observing weather and orbital motions, an interval of from 5 to 10 years is usually required to obtain adequate spectrographic material. Consequently, the list of well-determined masses published several years ago can be extended by only a few systems at this time. Furthermore, 2 of the stars on that list being re-examined And the last word may not have been said on why sig. In table 1 are listed values and masses of eclipsing binaries considered to be known without appreciable systematic error. Okay. Then the mean error is given obtained from the terminal agreement of the radial velocity should be significant values. Then the mean given should be the letters P following the mass in place of mean error indicates that the mass is not without appreciable scalar, but the analysis of the data is as yet provisional. Some of these values are from unpublished materials, estimates of masses of systems such as those as discussed in the next section is concerning the stars is required in order to interpret masses. Additionally, critical analysis given the radar and limits are not available from the systems values of the realism and they will be in a satisfactory manner. Less well determined values are followed by columns. Okay. Spectral types are from variety of sources, color emissions. Other properties of stars, this suggestions on the determination of masses. It is only by correlation of the masses with other properties of the stars that they may furnish observational tests of structural and evolutionary theory. It is customary to base such tests on positions in the mass, luminosity, and HR diagrams. Since the parallax is required for determining the masses of visual binary, its luminosities are readily evaluated. Then color and luminosity. Here's all of the tables you were talking about. Give position in the HR diagram. The systematic photometric work and analysis by Egan have provided the relevant information for many of the important visual binaries. Okay, so here we have these tables, or at least one table. Masses of eclipsing binaries. We have the star. Masses, I think mean error, radii, and spectra. And this is the masses, and the radii is of course given in how many suns. YYGEM is a main sequence system with similar components. Okay, so there are two of these, and that's of course why we have two numbers. So these are very similar. 0.58, 0.58, 0.02 is the mean error. Radii 061, and the spectra is M1. Unfortunately, that doesn't tell me anything about regarding the spectra, but that's cool to see. I mean, the mean error is pretty small. UV Leo. Okay, this one is a bit different. What was P? Did he say P was? Letter P following the mass in place of a mean error indicates that the mass is known without appreciable scale error. But the analysis, what? What do you mean scale error? That we don't have a mean error? Okay, F2. 2 point. Okay, so these pretty bigger stars. Oof. Pretty big. P mass is known without appreciable scale error. Analysis of data is or less well determined. Systems with unequal components. Of course, that's what we were talking about. These were that's why they were so similar. 2.8 and 1.4. Was it 5 from 4, 2.3? Okay, so less. Why would we not have the mean error, but we have an estimate of the mass? Subgiant systems. Here we don't have the spectra at all. How can we not have the spectra? Obviously, some light must reach us. No, okay, we know extremely little. Maybe it's a very unequal star, so we can't tell which one is what, the dominant one. But we do have a mass, and it doesn't seem that much bigger. Subgiant systems, system with giant, supergiant components. Okay. For an eclipsing binary, it is the radius rather than the luminosity that is usually well determined if the masses are known. The bolometric luminosities may then be computed if the effective temperature are known. For the stars near the main sequence of the spectral type about A5 and later, the correlations of effective temperature with color B2B and spectral type are well established. For the hotter as well as the more involved stars, the temperature relationships are less certain, and alternative methods of evaluating luminosities may be useful. So what is he saying here? So we know the radius rather than the luminosity, or rather it's the radius that is usually well determined if the masses are known. Okay, that's interesting. The bolometric luminosities, and I don't know what the difference between luminosity and bolometric luminosity is, may then be computed if the effective temperatures are known. For the stars near the main sequence, the correlation may be well established. For the less certain, such okay, so this is interesting. I'm gonna have to look that up. I don't know why we can only know radius or luminosity, or this seemed to imply that there's that such methods include an example is used to bending of the light into two components, blending of the light, the evaluation which has been most widely used for eclipsing binaries. In interpreting the positions of stars in mass luminosity diagrams, it is essential to know their evolutionary states, which are normally evaluated by the position in the HR diagram. Since the position of eclipsing binaries in the HR diagram are determined only with some difficulty, evaluation of their evolutionary states by other methods may be desirable. One such method would be the use of the intermediate band photometry. Another approach is to use the color radius diagram, since these two parameters are usually available. Departure of a star from the lower envelope of such a diagram would presumably show its degree of departure from the main sequence. Acknowledgements. Most of the spectrograms upon which the discussion in this review is based are obtained on the Mount Wilson Observatory as a guest investigator and at Lick Observatory. Okay. It's grateful. No, it's just observatory support. Alright, so we made it through. This was an interesting paper. It's interesting to see the reasoning. I also had to do a lot of homework trying to understand how this mass calculation is made, so I learned a lot doing that. Also, I thought it was interesting here in the end we started talking about the luminosity versus radii and stuff, because that's, I think, the next step I want to learn. Okay, how do we know now more about the star? So I have an idea now how we calculate the mass, so what else can we calculate? Additionally, it's, if you take a step back and just look at the paper and the author, I said it before, this Daniel Popper seems to be very, very careful. I even found some information on him, and yes, that seems to be also the legacy that he left behind. So this is great because it's the type of author that I wanted to read. However, it also makes the discussions very lengthy regarding the uncertainties and the measurements and the limitations of the instruments. So I'm gonna choose another author for the next paper just to get some other perspective. Maybe I'll have a look at Egan or something completely else. So yes. All right.